Today's video lesson is going to be over phase diagrams and how they apply to the different states of matter. So I'm going to do a quick review over what we have talked about this year so far when it comes to solids, liquids, and gases. So first of all, with solids, there is very low kinetic energy. The particles are barely moving, so this Ke just stands for kinetic energy. Solids have a definite shape and volume, and this is due to this low kinetic energy. So kinetic energy is the energy of movement, don't forget that. So there is definite shape and definite volume, and so at the particle, that is at the atom molecule level, the particles are very tightly packed next to each other and they are barely moving in place, okay? And so there is strong attractive forces between them. So they are really bound to each other, so strong attractive forces. Or strong forces of attraction is what we call this between them. So strong attractive forces between the particles, definite shape and volume, and low kinetic energy. Now, this is for a solid, so as we go towards the gas state, all of these things are basically changing. So all of the things that I mentioned, and of course a liquid is the state that is kind of moderate and in between the solid and gas states. But as we get to the gas state, we've got really high kinetic energy, okay? There is no definite shape or volume. Volume will take on whatever it really has no definite shape or volume. You can just really kind of capture it in a space, but there is no definite shape or volume. And this is due to weak forces of attraction. So weak forces of attraction between the particles. So you're going to see these terms, forces of attraction, when it talks about the particles in solids, liquids, gases. And gases, and you guys have seen the particle diagrams with gases, these are moving so rapidly and with so much kinetic energy that they are just sliding and bouncing and colliding past each other, and so the forces of attraction that would keep them close to one another doesn't exist. So very weak forces of attraction, very strong forces of attraction. Now between the solids and the gases is the liquid, where there is moderate kinetic energy, okay? So that basically means it is higher than solids, but it is lower than gases in terms of their energy of motion. Now, they have no definite shape, but liquids do have definite volume, okay? So they have a definite amount of space that they take up, so definite volume, all right? And their attractive forces are somewhere in between. They're not weak, they're not strong. They do still exist with liquids, all right? So it has what we would say moderate forces of attraction between the particles, all right? They just don't have enough kinetic energy yet to just totally slide past or totally separate from each other like in a gas state, okay? So moderate forces of attraction. All right, so this is just kind of an overview of things that we talked about, and yes, I'm writing down the slide because we're running out of room, but you guys have seen this before, right? This was in our last chapter, in our last unit, all right? Now, we're going to take this and we're going to now apply it to what is known as a phase diagram, okay? And we're going to use water. I know we use water a lot, but water is just a really common example, and it's a very good example in terms of describing particle motion and states of matter, all right? So over here in this phase diagram, you can see that we've got the most important things that you guys should always do when you are looking at a graph is to look and see what is on my x and what is on my y axis, because those are your independent dependent variables. Those are your variables whenever you are looking at or when you are graphing subject matter, all right? So in this case, this is water that is being studied, and you can see right here that temperature is changing Temperature is in degrees Celsius. So right here, this says 0.01, but you can pretty much say that this is like 0 degrees Celsius, okay? And this would be 100 degrees Celsius. This is 374, all right? So our temperature is on the x-axis. On the y-axis, you can see this says PVAP. This means pressure, okay, in atmospheres. So this is just letting you know that the pressure is being measured in atmospheres, kind of like the temperature down here is being measured in degrees Celsius, okay? So between pressure and temperature, we're seeing changes occurring in water, okay? So this whole area right here, for example, is water in the gas state. Do understand that anything in a vapor form is just in a gas state, okay? So this is gas, this is the liquid state, and this is the solid state, okay? Every phase diagram will be like this, okay? So every phase diagram. So some might look different where, let me fix it. All right, so every phase diagram is going to look a little different. So if I had the phase diagram for, say, carbon dioxide, it's going to look different. So we might see, and it just keeps doing that. All right, so we might see this being smaller, okay? So but this is still going to be what we call the solid, the liquid, and the gas section, okay? So this little wishbone right here section is always the liquid section. So it's always solid here, liquid here, and then gas here. So the solid's always hugging the y-axis, the gas is always hugging the x-axis, and the liquid is always going to be centered in between, okay? So that's important because it may not always tell you that this is the solid section of the graph, this is the liquid, and then this is the gas, okay? So just keep that in mind. All right, now, what you need to understand when you're looking at this graph is that each line is representing, each one of these right here is representing a phase change. Remember we talked about the 6 phase changes are condensation, vaporization, freezing, all of those, okay? We see those going on here. So right here, I'm going to give an example. I'm going to show you guys something. If you were to say, okay, at 0 degrees Celsius, which is right here, and 1 atmosphere of pressure, what's the state of matter? So what state of matter is water in at 100 degrees Celsius and 1 atmosphere of pressure? Okay, so what state of matter is the water in? So you come over here and say, okay, here's 100, here's 1 atmosphere. So if I go over here, all right, that's going to be this point, okay? Now, right here at this point, it is somewhere between, it is on the line that divides the gas state and the liquid state of water, okay? Now, so right now, we're not really sure, is this liquid or is this gas, okay? So if I say the temperature drops to 98 degrees Celsius, so let's say we drop the temperature to 98 degrees Celsius, then that means that, but we say that we're going to stay at 1 atmosphere, but the temperature drops to 98 degrees Celsius, then that means right here, 98 is going to be back just a little bit on this graph, all right? So it's going to be like, say, right here, okay? That may be, we're doing a little bit, but either way, we know that that's 98 degrees Celsius and 1 atmosphere. So now we are suddenly in the liquid section, okay? So we would say, okay, matter is officially a liquid. Now, if we were going to raise the temperature to, say, 102 degrees Celsius, all right, then that means that we would be over here. We'd still be at 1 atmosphere pressure, okay? And we'd be over here. Now we're in the gas state, all right? So you need to be able to read this graph in terms of pressure and temperature, all right? So any change in temperature or any change in pressure is going to affect the state of matter that you are in, okay? So let me clean up this for just a second, all right? Because we got a little bit too much going on. All right, so each one of these lines is going to signify each line is, or each curve rather, is signifying a phase change. So right here, this line is going to signify the phase change depending on which direction you're going, whether we're going from here to here, ice to water. That would be from a solid to a liquid. So this is going to be melting. If we talk about this way, that's liquid to solid. That's going to be freezing, okay? Which would make sense. If temperature is increasing down here, then yes, it's going to melt, all right? And then if we are decreasing temperature, then it's going to freeze, right? So the diagram represents things that we already know, and it's supporting that. This curve here is going to represent going from liquid to gas or gas to liquid. So this curve on the phase diagram is going to represent gas to liquid. That would be condensation. And then the opposing, liquid to gas, would be vaporization. So you can see how this phase diagram, so vaporization would be going liquid to gas, this would be condensation. This phase diagram, you can have one of these for any substance, not just water. You can have any substance being represented. And like I said earlier, the phase diagrams can look different depending on the substance. And of course, you have right here solid to, that is gas to solid, and solid to gas, which would be your deposition and your sublimation. So these are phase changes we talked about in the last unit. So with your phase diagrams, it's really important that you're able to know always, as I mentioned, that it's going to have these three sections. It's always the solid, liquid, gas. Solid hugs the y-axis. Your gas is hugging the x-axis, and the liquid is going to be like in between that wishbone. Now, and also be able to know that any changes in temperature or pressure can affect where you are and which way you're going in terms of a phase change. So if you are at 100 degrees Celsius and at one, let's say up here in terms of your atmospheres, okay, so a little over 1, all right, and then you end up increasing temperature, that's going to put you this way. So if you keep pressure constant, but you increase temperature, then that's going to put you in, that's going to lead to vaporization and put you in the gas section of the phase diagram. So phase diagrams are important to be able to read and interpret in terms of your solids, liquids, and gases.